Okay, so I guess we can get going. Oh, that echo's kind of disconcerting. So I'm Paul Berbick, your actual lecturer. Can you guys hear me? This lecture hall is extremely big for the size of this class. Yeah, so if you want to find me, I'm in the basement of the mathematics building. You can come visit me anytime. If you send me an email first, I can make sure that I'm there, but generally I'm free to help you guys if you ever need it. Before I get into this, is there any concerns or issues regarding the first two lectures? Get scared to do a good job? I'll take your silence as a no, so I'll have them punished severely. So today we're going to continue what we were doing. We're going to talk a little bit more about parametric curves and surfaces. I will be making these slides into course notes. I've been away at my sister's wedding for a bit, so I've already started this process. But these slides for the time being should be sufficient to do all the work that you've been given. Have you guys been able to log into that, what is it called? WebAssign, yeah. Okay, good. A lot of the time, if you think you have the right answer, well, if you suspect you have the right answer, ask yourself if you're typing it into the computer correctly. Because the syntax that is required is very specific. So you can't type in E. Is this better or worse with the microphone on? Too many opinions among this classroom. Yeah, so just make sure you're typing everything in correctly. So, okay, so let's get going. You guys are engineers, right? No. Who are engineers? What are the rest of you? Maths teachers. Okay, well, don't take your cues from me, right, if you want to be a good teacher. Okay, so consider the parabola, right? This is sort of one of the most simple, non-trivial curves that we can draw. Right, so you learned a couple weeks ago that what this is actually is a graph. That is to say, this is just some sort of visual depiction of a series of points on the plane. So we can take these points and instead define vectors, right? 2 points define a vector. One of those points will always be the origin. So in fact, we can regard the parabola as a collection of these vectors, and we can generate them by a vector equation given by RT is equal to TT squared. So this R is bolded. So whenever I use bold notation, that will typically define a vector. In your notes, or in your handwritten notes, since you can't draw something bold, it's typical just to draw a vector or a harpoon over it, if you'd like. Okay, so here's a few positions on the curve. If we look at R1 and evaluate it, 1 would get substituted in for t here, and you'd see we get 1 squared, which is 1, 1. If we substituted 2 in here, we would get 2 squared, which is 2, 4. 3 gives you 3 and 3 squared, which is 3, 9. And of course, we're going to get one of these points for every real t, right? So this is just an alternate way of describing the parabola. So in general, this vectored valued function is called a component function because it's given by 2 real valued components, right? That is, you give me a parameter t, and I'll return to you some point that lies in the graph of that function you've given me. It's like enumerating your way through the set of points in some sense. So the definition of a component function in 2D, so if you give me 2 real valued functions, x and y, then the vector valued function that takes a scalar, r, and returns a vector in R2 is given by this mapping. You give me a t, and I give you back an x component and a y component. Right? So again, this is called the component function, and specifically it's the component function given by x and y. All right, we usually use the letter t as the independent variable because it typically represents time. This should resonate with the physicists in this classroom. Namely, when t increases, we can really regard this component function as describing some type of motion in space. Right, so here's the point on the parabola at r at minus 1.25 seconds, which I guess you can move negative in time. That's r at negative 1, r at 0.75, r at a half, r at 0, r at 1, r at 2. So you can see it's sort of, we have this particle that's moving through the parabola. So in order to indicate how this particle is moving, we sometimes draw these little chevrons or this arrow to indicate the movement of the particle. Right? But really, you can imagine that these components are a way of describing a motion through space. And the arrow should always be pointing in the way that your parameter is increasing. Okay, so functions given by component functions are said to be in parametric form. Right, so I'll say component function, vector function, parametric function to mean the same thing. They'll be synonymous. We say this because points are retrieved through a parameter, t, though we will see that we can use more than one parameter. Right? We can see that every function, y is equal to fx, easily corresponds to the vector valued function given by this. Right, so any function that's expressible as y equals some function of x, you can easily parameterize it because your first parameter can simply be the parameter x, and you send it to your function, it gives you another one back. Okay, however, we are dealing with shapes that aren't functions, right? A circle isn't a function, right? Because it no longer satisfies the vertical line test. So how can we parameterize things like circles? Okay, so what is the parametric form of the circle of radius r? So think of what we have to do here. We have to give a description of the circle which relies on only a single parameter. Does anyone have any ideas what that parameter could be? Think to last week. What were you doing? Thank you. Okay, so last week we were talking about different ways that we could represent points in the plane. Right. I want to see all of you nod as if you're listening to me. Jesus, Murphy. Okay, so how could we describe points in the plane without a grid? You said spherical and polar. So how did we describe points in polar? Okay, a radius, no, radius and how many angles? Polar. Just one, right? So if I fix the length, how now can I describe all the points on the circle? What's the only thing that you need? Theta, right? Theta will be our parameter. You say, okay, make a stick of some fixed length and just rotate the stick in space, right? So instead of time, you're going to have theta. So we know that the points in the circle can be given by a single parameter, theta. So we have this trivial parameterization of the circle. So this is a fun game. Instead of having two variables, we've reduced our curve to one variable. And this is only going to be possible with curves. Right? We're going to need two parameters in order to get surfaces. But you can see the utility in this, in taking some sort of, well, if I gave you an equation of a circle, you don't have any movement information. Right? How are we moving through this circle with this parameterization? Well, what are the only two options? Who said that? A plus. Wait, 4? Whatever the grades is you get here, you get the maximum one for saying so. Thumbs up. So if we check a few values of theta along the circle, if we check 2, we know exactly which way we're going. I'm going to show you how to check 3. This is where we are on the circle at pi 8s. This is where we are at 2 pi 8s. This is where we are at 3 pi 8s. Who wants to do me a favor? All right, no one. I need to be able to fix these slides, and it's very helpful if someone can just take down the slides where there are errors. All right, I'll do it myself. Nice hustle, guys. Okay, so which way are we moving through this circle? Counterclockwise, anti-clockwise, right? So we can draw these chevrons in order to talk about how we're moving through this circle. But again, the name of the game is creating movements on curves rather than just describing the curves themselves. So counterclockwise motion. Okay, so here's an example of a parameterized curve which obviously has no representation as a function, right? Because this fails the vertical line test in like an infinite number of points. All these points are given by just taking some t. So here I am saying we go from t 0 non-inclusive to 12 pi, and we're moving along like this. And just so you can get a feel for how to work with these component functions, let's ask this question. Where does the spiral RT is the vector, whose first component is cos t over root t, whose second component is sine t over root t. Where does this cross the x-axis? Right? We know it does so infinitely many times. So who has an idea here? How can we determine where this curve is crossing the x-axis? What are true about all points at the x-axis? y0? Perfect, yeah. So if we cross the x-axis, all the points on the x-axis have a description like 1, 0, 2, 0, 3, 0, right? So what does that mean about this component here? Well, it means we have to determine when, for what t, does the second component become 0, right? Where is this y equals 0? How are you going to get multiples of pi out of this? Maybe we'll have multiples of pi. That's not clear yet, right? Because this is spiraling in. I think it's very clear from the picture that these aren't equally spaced, right? So it can't be simple multiples. It can't be integer multiples of pi, right? Because these are getting closer and closer together. But let's find out. I think you may be right with some caveats. Okay, so we need to figure out all the values of t so that the second component here is 0. Right? That is t, for which sine t over root t is 0, which we can easily solve. Right? So we can solve this. Sine t over root t is 0. Right? So we can just get rid of the denominator because that can only bring us to 0 if t goes to infinity. This means sine t has to equal to 0, which means that t is pi k such that k is in z. So that's probably where we're grabbing our multiples of pi from. Okay. And thus the curve intersects at the x-axis at these points. So a little bit, I'm reluctant to call these multiples of pi because they sort of disappear. Like once you take the square root of pi, game's over. It's no longer a multiple. Did I do this correctly? Yes. Yeah. Where does this numerator come from? Well, what's sine of pi half? Sine's this one. Sine of 0 is 0. Sine of pi half is 1. Sine of 3 pi halves is negative 1. Right, so we're going to be alternating between a positive 1 and a negative 1. Right, so this numerator here is just compensating for that sign change. Right, so at 2 pi, you have negative 1 squared, 1. Right, so when you're looking at this later, which you should, this is just to compensate for the sign changes, right? Because I could have just kept sine t up there, but I removed it because we're only evaluating sine at multiples of pi. Okay, so recall that the domain of any function is simply the set of points for which the function is defined. Right? That is, when r is equal to the component function, and this should really be x and y, but f and g are also okay, we have that the domain of r is equal to the intersections of the domains of the individual components. Right? So here's an example. What is the domain of r when its components are t cubed, ln 3 minus t, and the square root of t? Well, what's the domain here? Where is t cubed defined? Everywhere? Yeah, t cubed is defined for all values of r. Right? So there's no problem. What about ln 3 minus t? Well, what can't we take lns of? 0 and negative values. Okay, so 3 minus t has to be greater than 0, strictly. Okay, what about this? Oh yeah, our parameter is always going to be real. Okay, so t has to be, yeah, non-negative. Okay, so looking at the individual domains, so the domain is going to be the intersection of the domains, so the reals, union, so look that we're subtracting here, right? So t has to be at least, has to be as small as negative 3 and further, negative, right? because when we subtract it, it becomes a positive. Right? So if we take 3 minus t has to be greater than 0, we'll find that that's true on the interval negative infinity to 3, non-inclusive. I can't put t equals 3 in here. And the square root of t has the domain 0 inclusive to infinity. And if we take the intersection of these intervals, well, you can figure out about r, because r, the whole space intersect anything is just going to be the anything that's left over. So can we see that the intersection between minus infinity to 3 and 0 to infinity is 0 to 3 inclusive? At least a couple of you have to nod. Or I'm going to lose all confidence, right? Stop spending so much time drawing images. The limit of a vector-valued function is defined as the limits along the components of R. So we're used to taking limits of functions, right? And when we're taking limits of functions, what we were doing is we're sort of sliding along the x-axis and seeing how things were moving up and down in the y-axis, right? But this is only good for functions, right? As soon as you cross over yourself, those sort of definitions for the limit aren't as useful. So if we're able to parameterize the curve, then I can say the limits of the curve are the limits of the individual components of the curve, right? So speaking precisely, if RT is a parameterized curve with components x and y, then the limit as t goes to a, right, the single parameter, is equal to the limit as t goes to a on the first component and the limit as t goes to a on the second component, right? And this is all provided that the limit exists and that we're inside the domain of the function itself, right? But those details aren't too important. The definition of continuity is that if a is in the domain of R, then the function is continuous at a, provided that the value of the function and its limit are equal. So here's a simple picture. We're continuous here because if you take a limit into this point, you are defined where you would expect to be. This limit is discontinuous because the function is defined up here, but the limit would say that you need to be in this empty point, right? So discontinuous, continuous. Find the limit as t goes to 0 of RT, where R is the vector component function t to the minus t and sine t over t. Okay, so what do we do here? We're going to take the limits individually of both of the components. So what's the limit as t goes to 0 of t times 1 over e? Okay, so what's true about 1 over e, right, for any value of t? Is it ever not defined, 1 over e? No. It's always what? A number, right? So if t is tending to 0 and e's to the minus t is tending to 1, what is the limit going to be? Anyone? Even wrong answers I'll accept. It's something going to 0 multiplied something going to 1. What's going to win in that product? 0. So the limit is 0. All right. The second one's a little bit harder. Sine t over t. Who remembers this one? Okay, so we're the physicist in here. No. Who's a physicist? There's not a single physicist in here? Okay, engineering. What have you been told about sine on extremely small values? It's roughly the same value, right? If you take your calculator and take sine of 0.000000001, you'll get it back. The geometric meaning of this is that if you're looking at sine extremely close to the origin, it basically looks like a line, right? Just t. So telling you that sine t is basically t near 0, what is the limit as t goes to 0 of sine t over t? 1, right? Because you have something that's basically t over t, 1. And so that's how you do that one. All right, so I don't want to dwell too much on this because limits are something that you should be familiar with. But remember, you can always go look up tables. You can cheat supposedly, I don't really want to call it cheating because this is not cheating, just you'll often have to use table lookups to do some of these things. All right, so by adding an additional component, right, we can define curves in space. Right, so what I was doing right now, I was taking t and I was returning a point in the plane. If you give me t and I give you three things back now, I can give you a point in the plane and associate some sort of height with it. Right? So now I'm able to define surfaces. So a component function in 3D is if you give me an x component, a y component, and a z component, and they're all real valued functions, then the component function given by these is the vector function. RT is equal to xt, yt, zt. So it's the same game, except now that we're working in space rather than on the plane. We can extend our definition of limit onto these curves, which are called space curves, curves in space, provided the limit actually exists. But it's just the same game. You just take the limit along the individual components. Okay, so here's the spiral that we had before, and I'm just going to give it a z component equal to t. Right? That means as t increases, we're going to move higher and higher and higher linearly. Right? So if I were to take this and look at it from the top, you would see the same spiral that we had before. Okay. Where does this spiral go to as t goes to infinity? Right? So here's 0. And we're spiraling inward like this. Where are we heading? The origin's right here. Origin's here. 0, 0, infinity. We're at the origin, but infinitely high away from it. Okay, so that's our geometric intuition. Let's check that the algebra works out. Okay, so we deduce that the limit as t goes to infinity on this space curve is 0, 0, infinity, because I'm just taking the limit on each of these, right? So who cares about so the top here is bounded by -1 and 1, and if you divide that by something huge, it goes to 0. Sine t is bounded by -1 and 1. If you divide that by something huge, it goes to 0. And t is free, so we go to infinity, right? So that's what's happening here. Curve sketching. How can we sketch the curve cos t, sine t, t? All right, so here's the strategy. Forget about the third component. Forget about height for a second. What is cos t, sine t in the plane? It's like you're taking your whole space curve and smushing it into R2. Circle. At least one person's paying attention. So we have a circle in the plane, and what's happening as we increase t? Yeah, we're moving up and up and up and up and up. Right? Does anyone know what this shape is? Spring, or helix, I guess. So the strategy here is to see what shape is drawn in the xy plane, and the shape is the circle, and the resulting stretch shape is the helix. So it looks something like this. These take me forever to make, by the way, like forever. Right? But you can see what's happening. We're starting at the bottom, and we're twisting, we're moving up, and we're moving up, and we're moving up, right? And we're going to continue doing so. I'm doing it on a limited domain. Yes? Oh, we got a wise guy in the audience. Touché, friend. Touché. It takes me a finite yet extremely large amount of time. There's a different type of forever in Canada. That's defined to be finite. All right, so again, these are these space curves, right? And for you physicists or engineers, what you should really be interpreting this as is a particle moving through space. Right, if I had this one I can represent if I had some sort of rope and I tied a weight to the end of it and I started spinning it around like this and moving higher and higher and higher. Right, this is you shouldn't see these as curves. You should see these as movements of particles, right? This is the purpose of vector calculus, right, in terms of applying it to physics, right? So this is why we wanted the parametric t. So where are we on this curve in 2 hours from now? Right? Okay, so when you take two surfaces in space and you intersect them, right? So in this case, I'm giving you a cylinder and a sphere. The area that both of these surfaces are occupying, in most cases, or at least non-degenerate cases, the intersection that is left is going to give you a space curve. So this particular space curve is called Viviani's curve. Viviani was a mathematician. You could look him up. But the question here would be, or a typical question I can ask is, well, what is this curve? Can you give me a parameterization of this intersection? So given that the sphere, so I guess I put the sphere at the origin, and it has radius 2. And I put this cylinder not at the origin, but I've moved it by 1, right? Otherwise, so if I made a sphere and I just stuck a cylinder through it through the origin, what would be left? Can you imagine this? Take a basketball and cut it with a cylinder in the middle. Right? What do you have left? Sphere, cut it, and where are you intersecting? You intersect in a circle where you enter, and you intersect as a circle where you exit. Right? That would be easier than this, right? Because I just did it. Okay, we have to parameterize the circle at one height and at another. This is harder. So anyone have any ideas how we can progress with this one? Where do two surfaces occupy the same space? When they equal one another. Right? Another A+ student over there. So let's make them equal to one another and work things out. Right? We need to determine what values of t satisfy simultaneously. Right? We need to know. We need to come up with a space curve so that for every t, the space curve will lie on the cylinder and also lie on the sphere. Right? So here's the cylinder. So for any t, it has to be true that xt minus 1 squared plus yt squared is 1. And for any t, for the same base curve, we need that xt squared plus yt squared plus zt squared is 4. Okay. What is this? What can we do here? This looks very much like a... Well, forget that this 1 is here. What does it look like? Circle. So if I put the 1 back, the circle, but we've moved it, right? Just from its center being at 0, 0 to its center being at 0, 1. So what kind of parameterization can we utilize here? Well, we've seen how to parameterize the circle with theta. It's just a little bit more difficult because we've shifted it a bit, right? But we can just shift our polar coordinate system along with it. Right? So if I say that x and y get 1 plus cos t and sine t, we see that this satisfies the first equation here. Right? Because if I say 1 plus cos t goes into here, the 1's cancel, then you get cos squared t. If you take this sine t and plug it into here, you get sine squared t, so that's equal to 1. Right? So knowing that this has to satisfy both of these equations, I'm going to put x and y in from here into here, and what we're left with is simply z. Right? So all I need to do now is solve for z, right? Because we've eliminated x and y. So this is going to be a little bit tricky. Okay, so we need to solve for z. Okay, so 1 plus cos t squared plus sine squared t plus zt squared is 4. If I expand all of this out, I get 1 plus 2 cos t plus cos squared t. Right, that's from completing the square here. This is a sine squared t. So cos squared t plus sine squared t makes 1. What did I do with that 1? 1 and 1 make 2. If I take that 2 to the other side, we're going to... Oh boy, I shouldn't have skipped a step. Okay, so this is 1, and this is 1. That gives us 2, right? That's where this 2 comes from. Is there a board in here? Yeah. Is there chalk? Never chalk. Wonderful. Huh? Does someone have a whiteboard marker?
Actually, I do.
Oh, teachers. Yeah, I got it. If I write here, will everyone be able to see? Visible? 1 plus cos theta squared. I only need to do the second line. Sine squared theta plus zt squared equals 4. Okay. cos theta plus cos squared theta plus sine squared theta plus z t squared is equal to 4. Okay, telling you this is 1. So what do we get? We get 2. And since we have a 2, I'm going to do this. Right? So 2, 1 plus cos theta plus zt squared is equal to 4. And now I'm back on track. Right, because I'm claiming zt squared is 4 minus this. I'm going to keep this for a little bit. Not like you have a choice. You can always come down here and fight me for it. Okay. What I can do from here now, though, is convert this into a square by using the double, oh, where am I going? By using the double angle formula. Right, so you can look it up in your tables, but 1 plus cos t is 2 cos squared t half. Once I have this done, I can expand. You get 4 minus 4 cos squared t half. And 4 minus 4 cos squared t half is 4 sine squared t half, which is 2 sine t half when we take the square root out. All right, so all of this kajiggering was in order to get rid of the square on the left-hand side. Right? Because when you take square roots, you are in fact limiting the domain that you're working with. So you have to be careful about what operations that you're doing. Right? Suppose you divided by something, you have to then say, well, this thing that I'm dividing by can't be 0. Right? But since there was a square on both sides, we were peachy. Right? So the parameterization of this intersection is given by 1 plus cos t, sine t, and 2 sine t half. Right? And to prove to you, here's how we draw it. Right? This is what's left. Right, so the point here is that two surfaces, if you intersect them, they're going to give you some type of, they're going to give you a space curve in space. Right, the particular particulate movement through this is sort of arbitrary because we sort of stated where t equals 0 was. Right, we would have to shift everything, so if someone told us the particle starts here, we'd have to readjust. But here's an example of a closed loop, right? This thing is just going to go around and around and around and around. All right, so this is calculus after all, so what we're going to be worried about is tangent vectors. The sort of physical interpretation of this is, if you return to my rope and weight example where I'm doing this. If I let go at some point, the particle is going to move in the direction of its tangent. Right? So we could already do this with single variable calculus, but we're going to now redevelop it to work on these component functions instead. But the idea is the same. So we're not going to try and recover a slope. Right? A slope is a scalar. Everything that we're working with is vectors. So what we need to do is say, you need to tell me the vector direction of the tangent at some given point. Right, so how do you define a vector? Well, a vector is simply just defined by 2 points. Right? You take 1 point and you subtract another. So I want to find the vector that's pointing in the direction of this point to this point. And then I want to move this point into here. Right? And what's going to be left is the tangent vector. I don't know if this graph is drawn correctly because we don't really know what's happening to the magnitude of this vector. But we don't care about the magnitude of the vector. We only care about the tangent direction. In fact, it's typical to unitize these vectors. So here's the situation. We have xt and xt plus epsilon. We're going to take epsilon to 0 and see that this point will collapse into here. Some of you may actually care about the magnitude. I think these moments help you with like torque and acceleration, but for the time being, let's not worry. Okay, so imagine the parabola again. What is the slope of the tangent at 1? Okay, so the parabola is y equals x squared. The derivative is 2x, so the slope at 1 is 2. So what does slope really mean? Right? Slope is rise over run. So that means if the slope is 2, that means if we step forward 1 unit in x, we're moving up 2 in y. Right? This is somehow from the first lecture. So let's see how this translates into vectors. Okay, so what is the tangent vector at 1, 1 on the parabola rt t t squared? Well, this is easy. We just follow the definition. Right, so the tangent vector is given by the limit r plus 1 plus epsilon minus r of 1 over epsilon. That's just the definition. We just apply this limit individually to these components. So what do I have here? Well, r at 1 is 1, 1. If I subtract these two vectors, I'm going to get what? So we take this t and we square it, right? So this is where we get 1 plus epsilon squared. Here we get 1 plus epsilon. And if we subtract these, we're going to have an epsilon and then so this expands to 1 plus 2 epsilon plus epsilon squared minus 1, so the 1 disappears. If we cancel here, we're going to have a 1 and a 2 plus epsilon. And this epsilon heads to 0. We get the vector 1, 2. Does this comport with what we expect the slope to be? And what is this telling us? Well, we're saying at 1, 1, the tangent direction is this way. Right? If you take 1 step forward, you've got to move 2 steps up. This is a bad graph because it's stretched a little bit, but suffice it to say 2 should look longer than 1. But that's a geometric interpretation, right? You're saying, so instead of now having an equation of a line, this y equals mx plus b, we're going to give the line as a vector equation, a parametrization, right? A point, a direction, and a parameter, right? This is the game. We're converting everything into vector functions at this point, right? So on the parabola, the vector line at 1, 1 is given by 1, 1 plus t 2, 1, right? This is backwards. Is this backwards? It's backwards. Right, and the point is that you can combine this, and you're left with the component equation 1 plus t, 1 plus 2t. Right, so we can vectorize everything. Okay, so the idea of the tangent vector applies to component functions of higher dimensions as well. If we let r be a component function defining a curve, then its tangent vector at point rt, right, so remember that when I say rt, this is really indicating that we're on the curve at a point. Right? So I will no longer say the point x, y, z. I will say the point rt, right? Because we have a function which is going to give us an arbitrary point on the curve. Right? So the derivative of this component function with respect to t, sometimes written simply r prime t, is defined to be the limit as epsilon goes to 0 of rt plus epsilon minus rt over epsilon. Right? This is just the analytic definition. We're not going to use this. It's going to turn out that we can just use our derivation rules, right, in place of this. Okay, so let r equal x, y, z. Then dr dt is equal to dx dt, dy dt, dz dt. Right? This is just a proposition allowing us to skip using the limits. And here's a quick proof. By definition, we have dr dt is equal to the limit of epsilon goes to 0 of rt plus epsilon minus rt over epsilon. We apply this limit to each of the individual components and then just employ the old definition of the derivative, right? So the whole point is don't worry about limits. That's really only useful when thinking geometrically. It's much easier to just say that the derivative of y equals x squared is 2x. We're going to use algebra. That's the point. Okay, so the parametric equation of the tangent line then is given by, so if we want the tangent line at RA, we have to start at RA and then move in the direction of the vector tangent at A. Right, so it's very simple. What is the tangent line on the elliptical helix? Sine t, 2 cos t, t at r pi half. So this should be something that you're already able to do, right, given that I've told you this. Right, so we're going to need to determine what r prime at A is and RA is. All right, so note, the derivative of r is going to be what? Well, sine goes to cos. Cos goes to minus sine, so that gives us minus 2 sine t, and t goes to 1. All right, the tangent line is then given by r at pi half plus the parameter t, so in the direction of the vector, tangent vector r prime at pi half. So if I take this r prime and I evaluate it at t equals pi half, what do I get? 0. So cos of pi half is 0, sine of pi half is 1, so that becomes minus 2, and 1 remains. I then take these vectors and I can add them, so 1 plus 0 is 0. 0 plus minus 2 is minus 2t, and we have pi half plus t. Right, so here is the vector or parametrized version of the tangent line. Right? So here is this elliptical helix that we've been working with, and here is the tangent line as described as a vector. And notice something, right, that I have direction on this tangent. Right? As I'm moving through here, if I let go of my rope, this is the direction that the ball is going to travel in. This is how the geometry of these tangents look like from different views. Right? So if I take this and I look at it from the top, we're going to see this. If I take this and I look at it by eliminating y, just by rotating it a bit, you see this. Right? In fact, you're going to see these tangent relations in every perpendicular or orthogonal type of projection that we're doing. Okay, so surfaces now. A parametric surface, or a general surface in R3, may be described by a vector-valued function of 2 parameters. Right? So with 1 parameter, we were able to define curves. Right? With 2 parameters, I'm going to be able to define any position in R2 and associate a height with it. So following the definitions from before, if we let x, y, and z be component functions from R2 to R, the parametric surface defined by those components is given by this. Right? So here's R. Here we take 2 components, s and t. I use s and t, but some other books use u and v. So just be aware of that difference. So the parametric surface defined by these components is given by 3 components, an x component, a y component, and a z component, and you need to give me 2 parameters now. So here's an elliptical paraboloid. An elliptical paraboloid is a I'm telling you this because this is on your website, and only because it's on your website. There's some question that says, can you classify the following curve as an elliptical paraboloid or circular paraboloid? So an elliptical paraboloid is a paraboloid with elliptical cross-section. So so this notion of cutting a surface is very important. If you take a sphere and you cut it with a plane, right, we always cut by something linear. What do you have left over? A circle, right? These are these level curves that we're talking about in the first lecture. So if you have a parabola in space, just a regular line, and you spin it, right, and you let it arc out a surface in space, that's called a paraboloid. Now we can take this paraboloid and cut it and look at the shape that's left. When the shape that's left is an ellipse, it's called an elliptical paraboloid. When the shape is a circle, it's a circular paraboloid. And it turns out that we can parameterize these paraboloids via this transformation. Right? X gets a root s cos t, y gets b root s sine t, and z gets s. Right? And t and s come from these intervals. I'll give you a couple of pictures. Right? So here's a circular paraboloid. Again, it's just this parabola spun in space. And you can see if we cut it, it's going to leave us circles. There's an elliptical paraboloid. Again, it's just this parabola that's spun and then sort of squished in order to leave these elliptical cross-sections. So an elliptical cylinder is a cylinder with an elliptical cross-section given by the equation. Oh, so cylinder, not paraboloid now. Right, so again, imagine a cylinder. If you cut it, the typical one, you're going to be left with these circles, right, at all of these components. It turns out these elliptical cylinders can be parameterized by this. X equals a cos s, y equals b sine s, and z equals t. And moreover, if a and b are equal, we're left with a circular cylinder. Right? So this is the Cartesian representation of a cylinder, and this is the parameterized version. So this is somewhat important, right? In order to, if I asked you to give me a point on a curve, would you rather be given this, or would you rather be given this? What do you have to do to get a point out of here? To find an x and y that satisfy this? Well, you'd have to set x and then solve for y. What would you have to do to get a point from here? Just pick any s and t, right? And it gives you a point back. Right, so these are the points. Like, another nice thing about these parametrized curves is that they're just giving you solutions. Right? It's basically a way of numbering the solutions. We're creating an injection between the solution set, or the graph, and the real line. Right, so here's a circular cylinder. Right, if you see, if we cut it at any of these positions, we're going to get a circle. And here's the elliptical cylinder, and if we cut it, you will see that we'll get ellipses. How much do I got left here? A lot. Not a lot. Is there any questions to slow me down? Scarrett was giving me the impression that these were going over time. So I've explained everything perfectly. I can give you a test next week in the second hour, and it'll all be aces. Here's another surface parameterized in here, s squared t squared s plus t. And the way to sort of conceptualize these, again, is just by cutting it. Right, so you see, if we cut this at any z, so fixing z, to say z equals 6, is saying, look at the plane, right? What are the points that satisfy z equals 6? Well, it's all x, y, z, such that z is 6. Right? So you really get a plane. So if I fix z in here, that means s plus t is equal to z, and we're going to make a cut. And when you make this cut, you're just going to get a bunch of parabolas. This is sort of a neat surface. Okay, so what do we have to do now? Okay, so we have a tangent. Do you know what the purpose of these tangent lines are? Okay, one person's being honest. So in engineering, what do they tell you what these tangent lines? What do you think the purpose of calculus is? To confuse you. My God. So in single variable calculus, what was the gain? But for what purpose? So obviously in physics, if I throw a ball, these tangents are giving you trajectories. And that should be very, very clear. So from a physical perspective, tangents are very useful. Yeah, calculus can basically be described as the mathematics of rates of change. But what particularly were we being told if we had a curve that curved backwards? If I have a system, sort of the amount of money that I'm making, which can go up and down, what's the natural question to ask? You're an economist. You have some model. Yeah, you want to know how much money is it possible to make? What is the maximum value that my curve can achieve? So how were we determining these things? Tangents. Right? The tangent, we're really interested in where these curves are turning. And a curve will turn when the tangent is flat. Right? If we think of something else, remember how I was talking about sine and how on very small values it's the line? This is true of any curve at a point and its tangent line. So you remember these linear approximations? Well, I have some time to waste anyway, so let's talk about some of these issues because I'm hesitant to sort of waste your time by talking about something again. Do you guys care if I go back and explain things? No. All right. That marker. Do you have another color? I saw you had a box. All right. of values around here. Say at some time t. So you really don't care about what's happening anywhere else. You only care what's happening here. Okay? And you sort of magnify this, you're going to get something that looks like that. And if you magnify more, you're going to get something that looks like this. Right? And the point is, the further and further closer you look, the more that this curve is going to look straight. So how straight? Well, the straightness is given by the slope. It's turning into the tangent line as you look closer and closer and closer to it on the curve. Right? This is called linearly approximating something. Right? So if you remember, we were able to recover the line. Right? This line. This is the tangent line. The tangent line and the curve obtain the same value if we're close. And this approximation gets worse and worse and worse as you move farther and farther away from here. That's obvious. Right? So the point of finding these tangent lines is, in fact, they're allowing you to work with the same system and just treat it as a line. Right? When I say take sine of something small, don't even take sine, just make it linear. Wouldn't this be nice to do to all types of curves? Well, yes. It's called doing calculus. Right, so let's take a look at this. Some visualizations. Because it's useful to know how to plot stuff. So do you know that you can plot right from Google? What is happening? So I can say plots x squared. Okay. So we know that the tangent line here should be sort of a line, slope 2. So let's just keep focusing here. See? The line of slope 2. That's the point. This is true of every single curve. Now, will it let me do this? Perfect. Right, so visualizing surfaces is really important. Right? I didn't have Google back when I was in university. I was mesmerized the first time I ever used wireless internet. I was running around the library going, oh my God, I'm on the internet. There's no cords. I literally remember the first time I logged onto the internet. It was a magical moment. Okay, so we're on a curve here. So we're obviously not going to get a line. But what's the analog of a line in 3 space? A plane. So what should happen if I look really close to some point here? All right, so I don't know how useful this is going to be, but let's give this, oh boy, what's happening? Yeah, see, trying to visualize surfaces is difficult. I can't do it. Oh, what's this do? Anyways, just pretend. The point I'm trying to make is if you zoom into this curve enough, what you're going to see is that, actually, hold on. Can I restrict this? 2 to 2. 2 to, oops, 2, hold on. Minus 2, 2, 2. Minus 2, 2. 2. We didn't even have to go that far. That's pretty flat. Like Saskatchewan. Am I right, kids? My Canadian references are falling flat. Okay, but so this is the point, right? If you want to work on this curve, a surface especially can be extremely difficult to manipulate, right? They're complicated. But if you know you only want to work on the curve and locally, then we can replace it with a tangent plane and just swap it out, right? So this is one of the important uses of calculus, is that it's allowing us to have local approximations of curves and surfaces. Okay, so knowing that, what is the goal here now? Right? So we need to extend the definition of tangent vector to surfaces. And as I just said, a line is insufficient. We need a plane. Okay, so this is vector calculus. How should we describe the plane? You had it. We have vectors. I'm not trying to trick you guys. Just maybe on your exam, but definitely on your exam. It's all going to be tricks. Yes, we need to describe a plane with two vectors. So what are the three things that we need to describe a plane? Or two, if we're clever about it. You just described a vector. So if I give you a point in a direction, and you head in that direction, what are you walking? Put a line. The shape you're walking is a line. So you're almost there. How many directions do we need to be able to walk in to reach any point? Right, so if I give one direction, I can walk along this floor with a single direction. But if I want to move this way, what do I have to do? In another direction. In fact, any two directions which are collinear will be fine. It's nice to have them perpendicular, right? Like north, east, north and south would be insufficient. But you'll learn about this later in linear algebra, these types of bases. Okay, so we need two vectors and what else? A point. We need to know where we're drawing the tangent. Okay. So I'm going to give you the geometric interpretation of this tangent plane. Right? A lot of textbooks go through a lot of stuff to ultimately describe something that's quite simple. Right, so we're going to absorb this picture. Right, so you are attempting to find the tangent plane on a surface. Right? And we know how to take tangents along components. Right? Remember when we were doing partial derivatives in the first class? Right? I can tell you what the tangent is like in one of the directions and what the tangent is like in the other direction. Right? And since two vectors are sufficient to describe a plane, this is going to give us our tangent plane. Okay, one thing further. Have you been told this interpretation of the plane? So if two vectors, if you take their dot product and it's 0, what does that tell you about the vectors? That they're perpendicular. So I can characterize the plane as all points which form a perpendicular intersection with the normal to the plane. Right? So if these are two vectors giving you the direction in the plane, and I take their normal, right? So you're going to get a vector that's perpendicular to this and this. Then, if I choose any point in this plane and construct a vector to this point here, it has to be perpendicular. It has to be perpendicular to that normal. That being said, I can characterize all points in the plane using this relationship. Right? The points of the tangent plane are all x, y, z, such that x, y, z minus rst, which is this point right here, dot product, the normal, right, the cross product of the tangent vectors is 0. That is a relation telling you what all the points in that tangent plane are. Okay, well, how is this useful? Well, if r of st is a component function defining a surface, then its tangent plane is quite easy to construct. As easy as it was to construct the tangent line. You just have to do two things. Right, so I give you a point, or in fact I give you a point, but I give it to you by giving you two parameters s and t. Then the tangent plane at that point is just given by this equation. All we have to do is find the derivatives in two directions, specifically along the s direction and t direction, evaluate them at AB, take the cross product, and simply take the dot product with what remains. Right, but geometrically, if you're seeing so if you imagine a mountain, you move to some point at the mountain, and you point in two directions which are tangent to where you're standing. It's sort of arbitrary, but we always pick s and t. Then you're already able to describe the plane. Oh, I didn't put a pause. All right, so u squared v squared u plus v. Let's do this one. All right. So I have a curve. I say u tangent plane is given by what? Well, tangent plane given by all points x, y, z positioned at the point along the surface. That dot product with the normal to give a perpendicular intersection. Perpendicular intersection. All right, so what are the things that we need to do? Where did I want to take this at? I think it was 1, 1. 1, 1. So what is this at 1, 1? I have two parameters. So what's R at 1, 1? Wrong parameters. First component. One, right? So this is u is 1. So 1 squared, 1 squared, 1 plus 1. 1, 1. What's next? Well, we need the partial derivatives of this in two ways. dr by ds. Okay. Oh. So I switch components on purpose. This is something I find typical. That we'll teach using some variables and then swap it, and then everyone gets confused. And this is something you have to get used to, the fact that variables really can be named anything that you want. Or you have to think of these functions as like computer functions or machines, right, that are taking values and spitting something else out. All right, so what is the partial derivative of r with respect to u? All right, so what's the partial derivative of u squared with respect to u? Partial derivative of v squared with respect to u. Here. 2 plus v. 1. All right, what is this at this point, at the point u v is equal to 1, 1? Right? 2 times 1. The other one. dr by ds. What? Oh, dr by de. What's the derivative of u squared with respect to v? 0. V squared with respect to v. 2 plus 1 u plus v with respect to 1. Right, what's this again at u of v equals 1, 1? 0, 2, 1. Okay, what's next? Done? Could be done. We have a point in two directions, but typical to give these as a single component. Who remembers how to do this? Who remembers the name of this? Cross product. You guys remember how to do a cross product? What do you guys remember? Not much. Well, I'm really having to stop myself from over detailing these things, but okay. So we need to take the cross product of 0, 2, 1 and 2, 0, 1. I'll erase it. Maybe everything, but okay. Next time I'll bring some chalk, probably. Okay, so we want to take the cross product of 2, 0, 1 and 0, 1. Remember that that this is a determinant of something. Right, so what do we put in here? Put 2, 0, 1? 0, 2, 1? But what's in the first row? IJK, right? Unit directions. Where I is 1, 0, 0. A is 0, 1, 0. A is 0, 0, 1. Right? We did this because these are the unit directions here. Right? Forms our orthogonal basis that I was talking about earlier. Okay, who remembers how to take a determinant? Yes, you do karate, exactly. The what? I don't know what this is. We're going to have lots of cultural exchanges, right? Because we call it badminton in Canada, and you guys call it something different. Yeah, I'm not going to do that. I don't know what you're talking about. I remember the single definition of the determinant, right? That is you move across some row, so you take this, and you multiply by the determinant of what's left by covering everything else. Then you take J, and you multiply by the determinant of what's left when you cross everything else. Is that what you were describing? Sort of. Okay, but you have to remember that we have to alternate the signs. All right, so I'm gonna write this out very explicitly. So we have I, and you multiply by what's left when you cover out this and this. So you multiply by the determinant of 0, 1, 2, 1, minus, because we have to alternate signs, and these are really vectors, I guess. What do we get when we cross this out with this out? We get 1, 0, 1. Alternating a sign again, you get K. What's left when I cross this out and cross this out? 0, 0, 2. 2, 0, 0, 2. You know how to take the determinant of this. You're all just looking at me doing this. What I can do. Call A. Yeah, I get you. We're on the same page. I'm just giving you the language that you can use to communicate. Well, this is useful for you teachers, right? You can't stand in front of your class and do this, right? What is this called?
Yeah, but I'm not going to be teaching that to you.
We just pretend, right, for the purposes of pedagogy, right? What is this called? No. If I move, diagonal. What's this? Anti-diagonal. Anti and uncle diagonal, right? Main diagonal, off diagonal. So when you stand in front of a class and pretend to teach like I'm doing now, you'd say the determinant is the product of the diagonal minus the product of the off diagonal, right? So what do we get here? We get, and I'm going to convert to a component immediately. So the diagonal is 0, the off diagonal is 2. So this is minus 2. The diagonal is 2 minus the off diagonal is 0 with a minus. So that's minus 2 again. Here we get 4 minus 0, which is 4. Right, so this is giving us our direction. I think I probably did this wrong. On purpose. Did I do this wrong? Okay, so walking through what I just did, so we can give the tangent plane by this equation. Whoops. Did we calculate our partials correctly? 2, 0, 1, 0, 2, 1. Perfect. So we have this as 2, 0, 1, and we have this as 0, 2, 1. Also perfect. And we get minus 2, 4. Great. Right? So the tangent plane in the end is given by this, the dot product of these two vectors. Now, I actually think this is the optimal way to write a plane, right? Because it's like the essential components of the plane are staring you in the face. Right? Where does this plane go? What's one point this plane has to go through? What can I plug into here? So if you take a zero vector and you dot product it with something else, what do you get? Which scalar? No, you don't get a scalar. No, you do get a scalar, but which scalar in particular? 0, right? The zero vector is a 0 on the algebra of dot products. Okay, so how can you make this 0? 1, 1, 2, right? A single point which the plane is going through is there. You can read it readily. And here's the normal, right? So if a plane is defined by a normal and a point, really this is the best way to write it, right? You have the normal and you have the point, but it's more typical to write them like this, right? So this is the Cartesian definition of the plane. Okay, so here's our tangent plane, x plus y minus 2z minus 2. Right, so the surface that we're working with is this one. It doesn't have a name, but these are the two lines that go through it. So this gives you your plane. That means if I were to take that point, 1, 1, 2, and zoom in very close to it, that the curve itself is going to look like this tangent plane that we have described. And so it gives us this mechanism for locally working on surfaces. And it will have some implications for optimization and physics, right? If you want to know what the highest point of a mountain is, how could you tell that you're at the peak of a mountain? Well, yeah, so what does that mean practically if you can't walk? So this is an interesting question to ask, right? Suppose that you're just placed on a mountain, right? And they're saying, are you at some sort of peak? Or are you at the peak? How could you tell if you can't see yourself on the mountain? Well, it means that there's no more way to walk up in any direction, right? Can you see that? If you're like on a hump, no matter what direction you walk, you're going to go down. Right? That, in fact, corresponds exactly to our notion of flat planes. Right? So if you have a flat plane, you know that no matter what direction you're going to walk in, you're going to have to go down. Right? So we're going to optimize these surfaces in the same way we did curves, except we're going to use planes instead of tangent lines. What is incorrect? Can I conclude? What is the only thing you can conclude if you're at one of these peaks? Right? That if you know you can't walk in any direction without going down. Are you saying something about locality? Cool. You don't know if you're at the highest peak. Right? You don't know if you can walk off that peak and walk up one that's higher. You know that you're locally maximum, but you don't know that you're globally maximum. Right? So we're going to have to find all places on the curve which do this. And also we're going to be interested in these valleys. But the gradient in particular tells you the way to walk up the mountain so that you're heading to the peak the fastest. If you want the hardest climb up a mountain, you should travel in the direction of the gradient. Right? That's how you're going to climb the fastest. I'll write that into your notes. Yeah, I kind of went fast, I think, but you guys don't care if I let you out early, do you? Okay, so next week is double integrals and iterated integrals. Is there any questions regarding like the course in general or like administrative stuff? Next week I'll try to put more stuff into the lecture. It scared me a bit. Oh, from here to here?
Yeah.
It's just the dot product. So it's minus 2.
Yeah.
Hold on.